start and then I go. Okay, good morning everyone. Let's start again our activities in the School of Advanced Studies. Today we will have activities in the morning and also in the afternoon, but will be lighter than the other days. We have only 2 classes in this morning because unfortunately Professor Hilario was not able to join us due to some problems in Italy, but we will plan another for him a novel visit in the following weeks, and then we can advise that and we can talk with him properly. Today we have 2 lectures in this morning, Professor Federico and Professora Valentina, and in the afternoon we will complete with Professor Marcus and Professor Casey Jong. Okay, so I would like to invite Federico to join us. Thank you for being here again. I think it's more than 4 times, right? Yeah, more or less. Okay, thank you. Can I take that? Yes.
So, hello to everyone. Can you hear me well? It's okay? Good. So, my name is Federico. I'm from Denmark Technical University, Copenhagen, from Denmark. So, this lecture seminar is about alternative proteins from lab to industrial scale. So, the agenda of this presentation will be it's DTU, strategy and goals about Denmark Technical University, overview on proteins and functionalities, plant-based proteins, the market trends and the relative issues and problems, and industry and lab, which are the challenges in this plant-based. So alternative proteins, I took the decision only to present plant-based, but I'm working also a lot with insect. Okay. So the mission of DTU is to disseminate sustainable and value creating solution in the area of food science, of course for the society. So the vision of DTU, and the vision is 5 years. So now we are in the plan 2020-2025, sorry. And is to prevent disease and promote health, create sustainable technological solution, and develop new and better food products for a growing... Close like this?
Yes,
okay.
Because you send people online.
Ah, okay, sorry. For a growing population. Of course, we respect the UN goals, and in specific is climate action, responsible consumption in industry, quality of education, because it's a university, it's a technical university, and well-being and zero hunger. In National Food Institute, we have several departments, and we work in a synergy all together. So we work between technology, chemistry, toxicology, microbiology, epidemiology, and nutrition. In specific, I'm affiliated in food production engineering group, so we are in between fundamental and applied science. So in specific, I'm in between in the balance. So it's to design and development of sustainable and efficient food. In specific, we work on in this way, so application, function, processing, and structure. And how we tackle this is a mechanistic understanding of the interaction between processing, condition, and food properties, And we analyze all the data with the mathematical modeling and monitoring food production process at all scale, so from micro to macro scale. Our approach, if we dive a little bit more in another level, is encapsulation, health, ingredient, interaction and function, bio-based packaging, and valorization of side stream. As you can see, you move from nano to macro scale, and you can go back and forth. In my specific case, I work with ingredients, interaction, and function, and is the case of protein. So my field of research is colloidal properties of food proteins, alternative but not only, or also dairy and marine proteins. So now we dive a little bit more in this lecture. So I would like to define the learning objective of what you are supposed to know before to work with alternative proteins. So the purpose is to understand the challenge behind a formulation of a food system in the lab and industrial scale. That is the title of this presentation. Based on what? Based on the observation on proteins modification at different level and conditions, okay? And how? By taking the chemistry of proteins. So if you understand this, and if you dive in this point by point, normally you can understand and you can work with protein food systems in order to create new food or to change the existing food. So now maybe is quite repetitive for you, but I choose to present 2 or 3 slides about the chemistry of proteins. So it's really flying on the surface, but I think all of you already know this. So proteins, elementary composition, we have the carbon, the majority molecule. The monomeric unit is amino acid. And we have 2 kinds of structures, so globular and filamentous. And this is quite important because based on this you have different effects in food, based if you would like to make an emulsion or a gel or a foam, for example. Then we have essential amino acid and amino acids. And how these amino acids linked in proteins. Peptide bonds. So it's a repetitive unit of amino acid giving you the structure of the proteins. Oops. So how many structures we have in food? Based on the complexity and a rearrangement of amino acid, of the sequence of amino acid, we have 4 main structures. Primary structure is a normally sequence of amino acid, linear. Secondary structure, we have the beta sheet or alpha helix. Then we have the tertiary protein structure, 3D, 3-dimensional. And then the last one, the more complex, is the quaternary structure. So just to be aware, all or the majority of food proteins in a food system that we eat there normally each day are mainly tertiary and secondary structure. The last one is the DNA, the more complex. Okay? And then we have different kind of bonds, peptide bonds, disulfide bridge, hydrogen bond, ionic bond, and hydrophobic interaction. So this is main what happens when you have a repetitive sequence of amino acids. Then we have the strengths of these bonds. So based on what we deal with, we need to take in account the strengths. So the covalent are the more resistant to be broken. So if you make a cross-linking modification, you have covalent bonds. If you add water, probably you have hydrophobic, so are the less strong to change, okay? And then one important point of proteins is how they behave, okay? So we have denaturation, so you have the native state of proteins. Then you apply, for example, heat treatment, okay? And you have a denaturation. If you continue with the time, or if you increase the temperature, you have a complete denaturation of protein. So you lose all the functionalities. But if you stop in a specific range of time temperature, you can more or less come back to the native state. And this is quite important in a lot of food systems: gelatin, yogurt, emulsions, okay? So if you master this, you are able to work with different states of proteins. And then you have other factors that affect the behavior of proteins. pH, salts, so ionic strengths, redox reaction, temperature, as I said, and pressure also. And based on the bond type and the factor, you have different answer of protein in a system. So which is the main message of this? Is if you understand the physical, chemical, biofunctional, and technofunctional properties of proteins, as well as the interaction between themselves, you are able to improve the performance of food system. So why I'm explaining this? Because imagine that you work in a company, you deal with proteins, and suddenly you change the raw material. Okay? What happens? If you don't master the process, maybe you apply the same treatment, but you have another answer, but you don't understand why. So you need to stop, you need to come back, and you need to understand. But if you have this knowledge, you are able to adapt the process. So the process will be, how can I say, tailored based on the raw material that you have. Then we have the functionalities. So we just take a look in the characteristic of the system, and we have the characteristic of the environment. So the system is the food proteins, the environment where the protein is located. And then, for example, you have dairy, bread, meat, and fish. Just a few examples. Then you have the environment, so pH, ionic strengths, and temperature. When they combine all together, you have interaction and different functionalities. So the system reacts in different ways. And then you can determine the solubility, water holding capacity, gelation, viscosity, and texture. Okay? Based on this, you define the colloidal properties of your system. Emulsions, liquid and solid foam, hydrogel and oleogel, the main colloidal system that we have in food. We take few of these now because it's quite relevant for this lecture. So the solubility, here I have the solubility as a function of the pH, and the solubility decreases when you are close to the isoelectric point. So when you have a system close to pH, we can say 5 in general, you have low solubility because you don't have different in charge. So the positive and negative charge are the same, so you have the aggregation and the precipitation. One example, take a glass of milk, add lemon inside, a few drops. What happens? Protein aggregates, you have a sedimentation, and the milk become white. So this is the effect of solubility and the isoelectric point. Water holding capacity is protein-water interaction, hydrogen bonding dipole interactions. So you have, we have the binding system to water, and again here, water holding capacity as a function of pH. When you are close to the isoelectric point, the water holding capacity is very low. So your system is not able anymore to retain water. It's what happens in yogurt, for example. You have the water on the surface. So you need to stay far from this area. So here or here in general. Gelation. Gelation, I think all of you know this when you prepare some cakes, for example. You use this slice of gelatin, so based on fish gelatin or pork gelatin, and this is a gelation process. So what happens? You have denaturation between 25 and 40 degrees Celsius. You have the unfolding, and then you decrease the temperature, so you put in the fridge, and then you give the shape to your cake, okay? Or at least the slice of gelatin cover exactly your cake. And this is what happens. So collagen, then you heat up, you have a denaturation of the system, and then you cool down and you have a new structure. Viscosity and texture. This you have in bread, for example. Okay? So protein can be viscous but also elastic. Is the viscoelasticity of the system. And how we can do this? When you have flour and you add water. What happens when you make your bread? Become like a dough and become elastic. This is the role of proteins inside. So more your system is rich on protein, more the elasticity change. If you don't have this protein, you can't do this. The quantity of protein is important if you would like to make bread or pizza, for example. The quantity of protein change because you need more or less elasticity. Then here you have elastics which recoils when it's released. So you stretch and then you release and you come back. And then, which is this macromolecules? Gluten. So based on the quantity of proteins, between 7 to 9% or 14 to 16, you have the firmness of your system. Then we move to the colloidal properties, emulsions. All of you, or I hope most of you know this, droplets of oil in water or droplets of water in oil. Oil in water or water in oil emulsions. Simple system. We only take this, but keep in mind that we have oil in water in oil emulsions, or double emulsion. And here is Pickering emulsions. So you put nanoparticles around the droplet size and you stabilize with these molecules. And this, what happens? Which is the role of proteins at that level? The role of proteins is to put to the interface between oil and water or water and oil. Then the challenge is to keep stable this emulsion. And the main factors are the charge. So more is high the charge, more the repulsion is higher, more your emulsion is stable. The size, so the spherical effect of the protein, and the affinity between the protein themselves or the protein with water or oil. Foam, liquid foam. Foam, you can add up to 99% of air, so 1% of liquid inside. A large bubble that broke is in the smallest one, protein content between 0.1 and 10%, and structure, again, of the proteins. So emulsions, you have oil in water or water in oil. Foam, you have the air. So it's liquid and air. How you can stabilize this? Proteins go to the interface and stabilize this bubble. And you have several effects that destabilize them, is the gravity, pressure, evaporation, diffusion, or fusion of bubbles. And here you have different scale, cappuccino foam, macro scale, so you have this one is air, this one is the liquid film, and these are proteins, agglomerates in the vortex, this one. And this is the liquid film. So 3 different scale of foam. And this is what happens when you drink a cappuccino, for example. You have this structure. And solid foam. So which is a solid foam? It's a liquid, is like a liquid foam with a solid structure, so very easy. The example that you know, marshmallow. Marshmallow is solid foam, so it's something that avoids the effect of gravity, so the structure keep stable. The gelatin, for example, a helix of helices, because the gelatin is the most common used molecules to produce marshmallow. This one. Then we move maybe to a more interesting part. So the alternative proteins. So until now I just make a recap on proteins and what we can do with. So now we go in the other level, so industrial scale, what we can do at that level and how we can handle with this. So plant-based food, we have some data of 2022 in Europe is a hot topic. So plus 21% in increasing in terms of money. In Denmark is, how can I say, specific country where they invest a lot of money in this green transition. So we have a lot of funding now to accelerate from the meat to the alternative proteins. And plant-based milk is the most developed category market and increasing in plant-based meat with a lot of issues and a lot of problems. So what we can say? We can say that the market is growing. The consumers ask for a wider choice of products because, as you remember, a few years ago, now is more than 20 years, behind meat entering the market with these burgers. But then at one point, consumers were tired about this because the product was always the same and they asked for different solutions. Then, which is the consequence? That in the 10, 15 years, we move quick and dirty. So we move directly to the production without understanding what happens in the lab scale. So plant proteins from lab to industrial scale become plant proteins industrial scale. So we produce, we texturize plant-based protein, we obtain burgers or whatever, but then we don't really understand what happens in this complex system or complex texturization of proteins. And the problem, there are a lot of problems because there is problems in taste. Maybe you don't want the taste of grass, of plants. Texture, Color, because it's green, is dark green due to the presence of polyphenols. Price, because sometimes it's expensive, so it's not really an open market for all the consumers. And based on what you are using or what you use, the nutritional value. So you miss or you lack some essential amino acid. So how to solve this? We come back to the lab. So we come back from the initial point. And here is a quick research that I did with PubMed. Just plant, with the keywords, plant proteins, food applications. Here you have the years, and 2000, 2022, as a function of published papers, so peer-reviewed manuscript. And as you can see, you have mainly two trends with the slope changing in 2012. So what happens? What I said before, so people come back to the lab, so come back to the company, come back to the academia, and they start to understand what happens. So the number of publications increase a lot. So we came back to the lab, and here I will present few of our work that we already published in our department, in many of my projects. So, for example, aquafaba. Aquafaba is the cooking water of chickpea. When you cook chickpea in water, you have already an extraction of proteins because it's hot water, and then you have an extraction of proteins. So until now, they throw up, but they start to understand, they start to dry, and start to recover these proteins. And what we did here, so we changed the temperature of boiling. Of course, 100 degrees the maximum, but we changed from 80 to 100, the ratio and the time. And then we spray dry, and then we create a foam. So this could be a simple example of recovering, we can say, waste from food processing. This one that you probably know, Ora Pro Nobis, is a project that we did the last year with a colleague, visiting professor from UFSCar in Copenhagen, in the DTU. So this one is a review that we published. We have few papers ongoing now. And Ora Pro Nobis is a plant rich proteins, up to 20% of proteins dry matter. The main issues of this system is to extract proteins because they bound with complex polysaccharides. So the main issue is to cut them. But we manage with some green approaches plus solvents or plus solvents alone. And then you have a huge source of proteins to use it. Then here is pea protein. So pea protein with commercial pea protein, we solubilize, so we took the soluble part of this pea protein with a simple process. We apply an enzymatic treatment, and we obtain this soluble and enzymatic treated proteins, so peptides almost. And then we check with the double wall ring technology, so it's the advanced rheology approach, the interfacial behavior. And then we add different concentration of salts, so we check the effect of ionic strains of the protein. And as you can see, you have different behavior at the interface. So why this is important? This is quite fundamental, but you can understand how the salts affect the protein behavior. For example, if you would like to prepare a milk beverage and you would like to add some salts, you know that you have different behavior of the system. Then this was another project with sunflower proteins. So as you probably know, sunflower oil are obtained by press the sunflower seeds. And then you have the oil. This cake, that is called cake, now is a waste. So they feed animal with this. But this is rich in proteins. So what we did was the extraction of this protein and then the dephenolization. So was before and after. And then we check the colloidal properties in foam and emulsions. Then, with the same proteins, we applied some treatment, like ohmic heating, to increase the hydrophobicity of proteins, so to be more react in a solution. And here we have the example of the intensity as a function of wavelength for different treatment. Then, since 2 years, we move in hybrid system. So hybrid system is alternative proteins plus, we can say, original proteins, like dairy, fish proteins. So what happens when, the question was, what happens when you mix two kinds of proteins and then you prepare, for example, an emulsion, a foam, or a gel? So can we replace partially or totally? And these were the results. So this we apply ultrasound on a mixed system of pea protein and casein micelles from dairy. And then we create a gel, and then based on the treatment and on the ratio, we have different gel porosity, different combination and different reaction to the ultrasound treatment. So we can modulate the strengthness of the yogurt, for example. The hydrogen is not yogurt. Then here was with pea protein and dairy in suspension. So different concentration and different behavior in your beverage. And here was pea protein with fish skin gelatin. So this is different pictures of oil droplets. This is oil. And these are the proteins. So you have the droplets is the oil and around are proteins. And we saw that we don't have, so this was a negative answer because there is no interaction between pea protein and fish skin gelatin. So it was not the best results, but it was an answer. So our approach, as I presented before, and then how we can move to industrial, really big scale. So how we can create new food system from lab to industrial scale. And here I choose to put 4 slides about finished projects that we had in our lab, that we create in a lab and then we move to an industrial scale. So these are projects with companies that I am allowed to show you. So there are no under patents or no papers. So this is a vegan mayonnaise. So a company called me saying that they produce mustards. Mustards you produce from mustard seeds, you boil, and then you take the seeds, you grind, and you have the mustards. Okay? But when you boil, you have the same effect than aquafaba, so you have a lot of proteins inside. So we take this water, we spray dry, so we take off all the water, and then we add proteins, and we make a mayonnaise. So we add only oil. And this was the results. Sorry for this. I always forget to say to people that I present this, because which is the results of this? This is, the texture is the same than a normal mayonnaise with eggs. The taste is not the same, but when you have the texture, the taste you can change easily. But this was only proteins and sunflower oil. The texture was the same. This one is from fungi biomass. So we extract proteins and we make an ice cream. This is normal ice cream. Normal is plant-based ice cream, commercial. And this is from the proteins from fungi. And the melting process is very slow for these fungi. And especially in a country like Brazil where it's very hot, this could be a huge advantage. Because your ice cream melt in less time compared to the commercial one. Then we had another problem. It melted very long time. So it was like a stone. But we are working on this. This one, frozen beverage. So we prepare a cocktail without water or alcohol. And then we create these small balls with liquid nitrogen, drop by drop. And then you can store in a fridge for more than 1 year, if you want. And then what happens? We work on the quantity of sugar, salts, and proteins. And then we manage to change the melting process. So we are these balls, a fixed amount of these frozen balls in a fixed amount of water or alcohol melt in 20 seconds at 20 degrees. So imagine that you would like to prepare something and this melt and in addition is cold. So you have double effect. This is juicy with a lemon inside, and this is Bloody Mary cocktail without the alcohol. And then I think is the last one of this project. This is a sweetie from Denmark, is a flødeboller, and is egg, foam egg with chocolate, with the biscuits here. And they asked me to replace this egg with plant protein. And we managed to do this. The main issue was that at the beginning the foam collapsed because it was not stable as with eggs. So we work with the quantity of salts and sugar on this. So the ionic strains. So just to finish, where or in which direction we are moving now. Employment of green technologies and modeling to move to the industry 4.0. So the creation of smart system. We have a lot of data now. So we need to understand how to optimize and which information we can take from this. Instead, we have millions of results, which is the main message behind this, or how we can optimize a food process. And employment of green technology, we have like green technology, I use in my specific case, ultrasound or microwave, ohmic heating or pulsed electric field to extract proteins from complex matrix like plant. Instead to use solvents, you use ultrasound and water. The yield of extraction is not the same, but you can avoid the use of solvents that then you need to treat again. So this is an optimization. Or, this is from my colleague, modeling. So we couple the lab or industrial with the modeling approach. And this prediction, obtain deep inside, optimize and control the process. So modeling enabled to create innovative solutions for product and process development. So this, I think, is the last one. I took the same slides that it was at the beginning, the learning objective. So if you understand this one, the purpose based on this observation and how to do this, you can handle with proteins. So I hope you have the answer after this presentation, and thanks a lot for your attention.
Thanks, Federico. I would like to open the audience for questions. You want to ask something or add something? Okay.
Well, thank you very much for the presentation. I work on the other side, on the dark side, for the animal protein. But my curiosity is about the timing. I know there is a huge work, mainly on the green extraction technology. I'm already using it in animal feed, so it's something that we are working on. But in your opinion, how much time is needed until this will become real? Because I know now this product can be sold to be more environmentally friendly, but is not at the end of the day by now, but they will become. So how much time we need to be ready to embrace this green technology and avoid the use of solvent, which actually is a huge problem?
Thanks a lot for your question. Which answer you would like to listen? The point is, these green technologies are not new. Pulsed electric field, ultrasound, we know, but how to use them is new. Pulsed electric field were used in potatoes to inactivate the microbiological activity, if I'm not wrong. But a few years ago, they discovered that we can tailor the colloidal properties or to extract this protein. Now, we are at the beginning. I give you some example. For example, with sunflower, if you extract with harsh solvents, in the huge volume, you can extract up to 90% of proteins from the cake. If you apply green technology, the maximum is 30%. So then the point is, or the question is that enough for you because it's a byproduct, or you would like to improve? We apply also a sequence, like pulsed electric field, ultrasound, microwave. And we can increase, but is depending of the system. Some proteins react in one way, some proteins react in another way. And with ultrasound, we can say microwave, pulsed electric field, and ohmic heating are gentle approach. So you can separate hydrophobic interaction or ionic interaction, but if you would like to really cut proteins from complex carbohydrates or fibers or whatever, the best is ultrasound, that we can use it. But then if you apply a huge treatment in terms of intensity and time, then you destroy the protein. This is the main issue. So you can apply even 1 day of treatment, but then what you recover is not useful because you can't do anything. So you have the aggregation, you have the precipitation, you have this formation of agglomerates. And I think takes a little bit of time, few years more. Pulsed electric field we have in our lab, we have in batch. So you charge, you apply, and then you take off, and in continuous. But in continuous, you need to have pump first, and the second, you need to work in a specific range of viscosity. If you put honey inside, something like that, you stuck the machine completely, so you need to stop. You need to, there are some adjustment to do, but we are working on this.
Okay, thanks. Djamel?
Hi, Federico. Thank you for your presentation. It's not really my topic, but as a general consumer, I have one question, if you don't mind. So I understand a lot of things in terms of technology, just to bring new things in the field, in terms to fit with the ecological needs. Nevertheless, the question that I have, in terms of the consumer behavior for the other sources of proteins. What's exactly your opinion? And second question, because you know, animal proteins is something that it has a huge history everywhere in the world. So shifting now to new sources is something that we can understand, we can explain to, as you are doing for students. But when you come to the countries, different countries of the world, maybe this aspect is not necessarily well understood and well accepted. So if you can help us to highlight on this huge and endless question, I will really appreciate. Thank you.
I try. So thanks a lot for your question, and it's a good question that a lot of people ask or they are aware about this. Because as I told you at the beginning, was my choice to don't present you insect proteins. Insect proteins, they start many years ago because it's an Asiatic country, is common to eat insect, but we are not use it. And will be very difficult, especially for our generations. maybe the next generation will be the case. I give you an example in this. In France, there is the big company Insect. They start with for humans, and then finally they choose for economical reason to move for feed for animals. The same in Denmark. We start few projects with insect proteins to replace or partially replace meat. The product was okay. We did a salami where we replaced 10% meat from the pork with proteins from insect. It was impossible to discriminate in a blind test. Impossible. But when you put, and it's mandatory, and thanks to this to put that in when you sell a product that you have insect inside, the acceptance is very low. And a lot of companies in insect, they change in Europe they come back to feed for animal. Concerning the plant-based, there are other issues: color, texture, texturization, variety of products. That is quite difficult because these proteins bound to polyphenols from plant is the green dark color of proteins, and this one is very difficult to take off. There is a huge investment from Novo Nordisk in Denmark, that is a pharma company. They inject, if I'm not wrong, 200 million euros in 5 years for free for university to accelerate from fundamental point of view the green transition. So we understand the fundamental, we can work on the final products. Dairy and meat is present, especially in specific countries, I think like Brazil. So it will be quite difficult to cut partially or to change the habits of people. And also in Europe, because in Denmark there is Arla food. Arla food is like Lactalis in south of Europe. They are big companies in dairy. So now they are working in a hybrid system. And then the last point is, I don't need an answer. Think about this. If I show you a yogurt made with dairy from cow, close to a yogurt made with plant-based protein, and a yogurt made with insect, which one you choose first? And which will be the order? I think, I don't need the answer, I think will be dairy, except I'm talking in general, if you don't have food restrictions, of course. I think you choose dairy, plant, insect, probably. Even if the insect and the amino acid sequence of insect is more close to animal. Plant lack in some amino acids or in specific quantity, so we need to counterbalance this. So it's a good question, and I don't know. I mean, and then it's the role of marketing also. At one point to say, we need to consume this because, and then first is the science, of course, but then we need to, to put this product in the market. And this, I think if you make a yogurt and you put a picture of an insect in a supermarket, I don't know in Europe if a lot of people eat this. And just to finish one second, and I had a presentation about insect 1 year ago, and the company was invited. So they cultivate and harvest edible insect, and we tried the chocolate bar. It was very good. So impossible to distinguish because chocolate covers the taste of insect. And then we eat tacos, I think, with insect instead of meat. After 1 or 2 minutes, I was in the middle to finish these tacos, and then I had a sensation of fat in my mouth because this insect contains 40% of oil. And if you don't have a defatting process or partially defatting process, at one point you are saturated because then you have a layer of fat in your mouth. And then you think that is insect, then make the conclusion by yourself. Please.
Thank you. I think it's an endless debate because myself, I grew up with the idea to eat beef and beef, you know. Yeah, you know. And now it's I reach part of my life just we can see this shift. But I'm trying just to figure out how to explain with the people coming from my community, just to explain them how to go to these new sources. I know about insects. I have been in Mexico evaluating projects for some universities, and it was already in fashion like 10 years ago. So nevertheless, what I'm scared, because just maybe in decades or just to go to proteins produced chemically, just to say. So this is the new way to feed people. You know, it's a debate, it's just philosophical.
And, yes, I understand. And then there is, I mean, we can talk all day about ultra-processed food. There is still this debate if we are at this process is still safe nutritionally and all these parameters or not. Is a big debate on this, but for example, in Denmark, in the canteen, in the university, they almost completely cut the meat. So it's only vegetables. If you do this at one point, you push, I mean, there is no choice. You eat, or you die. But then is our role to change. I mean, as a food scientist, food technologist, microbiologist, chemistry, to propose alternative. So, and where we come back to how to modify these proteins. Maybe you modify the color, the structure, and then you have a choice of products, the taste. Because with plant-based, and this is another open question. I don't know if most of you did already try the plant-based ice cream, Häagen-Dazs, for example. Check the list of ingredients. They can't make, now is very difficult or almost impossible to make an ice cream, a stable ice cream, without a lot of compounds, stabilizers, making of flavor. So you need to add a lot of substances, a lot of ingredients to give texture, cremosity, stability, color. Problem that we don't have with milk from cow because we have fat inside and we have this taste of fat in the mouth, so that is well balanced. This is a big challenge. And when you eat, we had a project, another project with I think, chickpea protein to make an ice cream. After 3 spoons, and I eat a lot of ice cream in my life, after 3 spoons, you have the taste of grass in your mouth. So it's like to eat grass from outside. And then you stop. So, and this, because you don't like anymore, and then you would like to drink water or other things to change this taste in the mouth. So this is another big problem, the presence of polyphenols and other compounds. So it's like this.
Okay, Federico. Any more questions? Okay, Wendell.
Thanks, Federico, for the nice presentation. I would like to know your opinion about precision fermentation for this, in the context of the plant-based market.
I'm sorry, but this is not really my field, so I don't want to say something wrong. We have, I hope it will be granted a project soon, and is about, what can I say, is precise fermentation to modify the techno-functional properties of proteins, and then when they are modified by precise fermentation, you texturize them with an extruder, and then you have, how can I say, modified but in a natural way, these alternative proteins, and then maybe you have different, how can I say, texturized product in terms of texture, color, dimension of fibers. But this I don't have an answer. And I don't want to, I mean, it's not my field, I'm sorry, this precise fermentation.
Okay, thanks.
You're welcome.
Okay. Yes. Here first, and then you.
Hi, thanks for your presentation. I really enjoy it. And my question is aligned with Djamel's question. So we know that this ultra-processed food may have some issues with human health, and I was just wondering if this problem of adding a lot of compounds into a new food is because we are trying to imitate some animal food source. And so thinking in this sense, what is your opinion about, like, if we stop to try to imitate some already existent food and try to create new like really plant-based food? Okay, this is plant. This is not a meat-based. It's a plant food that imitates meat or whatever. Like, okay, this is plant.
Yeah.
So we will be able to add less compounds and maybe think in a healthier ultra-processed food.
Yeah. Okay, thanks for your question. We work a lot with this, so we add a lot of compounds to imitate, because a lot of people are not, me included, we are not ready to eat like that. I mean, you eat, I don't know, eggplant, zucchini, but you know it's natural, you clean, you cook, or you eat like this, I don't know. But if you would like to target a lot of people or more people, you need to propose something that is close to meat analog. When you eat a burger in a barbecue, you can eat also eggplant. I mean, you grill and you eat. But someone who, for health reason, cannot eat any more meat, or for your personal choice, what you prefer? You prefer something that is close of what you ate before. So we need to propose, or the companies propose, something that is more close to a meat analog. Then I completely agree with you that maybe it's better to eat like this, vegetables, instead to apply a lot of treatment. This debate about ultra-processed food is quite controversial because in one side they say it's okay, so it's better, in the other side it's not good. Apparently now they define that there is no effect, so it's not good, it's not bad, you can apply. It's in the middle. But to answer that, to finish, this is the kind of approach. So if you would like to target more people, for example, another approach, if I have a colleague in Wageningen in the Netherlands working with oleosom. Oleosom are oil from plants. And he works a lot with a project close to elderly people that they cannot swallow anymore. So they charge a lot with oil, and when you put in your mouth, just go down. But you have the same feeling that like biscuits or meat. So it depends of what you would like to do. There are many questions. What you would like to do, what people would you like to target, which is your objective, and for who you are working. In academia, we need to be transparent. So we need to say, this is like this. You like or you don't like, is like this. Companies, maybe they have another approach. I'm not saying that they are bad, but maybe they target based on the market. It depends of what you would like to do.
Okay, Amin?
Thank you. I think you have answered most of the questions, but the thing is that I still have a kind of concern. So when I, let's say, go to the grocery store and buy a plant-based patty, for example, for burger, and I see like 50 or 60 different ingredients on the labels, and that makes me feel really concerned about the safety and let's say the nutritional value, whether it's giving me the same nutritional value or whether it's safe to eat, because we don't know, some of these chemicals might have long-term effect. And so what is your thought about that? Just
Thanks for the question. This is another good question. I don't know. Normally, if they are in the market, I hope they are allowed to be. So this is the big project that we have in Denmark. So how understand the proteins behavior, sorry, and to avoid all these, how can I say, these compounds that you need to add to mask something or to be more, how can I say, sexy for the consumers. Otherwise, if you see the burger dark green, I don't know if you buy. And then maybe the taste is not good, but I don't know. Is a good question. I don't know the long-term effect. I hope there is no long-term effect. But like this, I can't, I'm sorry, answer to you.
Yes, just to add something like that, I have this concern too. But we, at least as a food inspector professor, we assume that it was checked by the health agency and it was considered safe. But we know, I know what you're meaning. Depending on the number of the ingredients that you might have and the chemicals, I think it's difficult to predict what's the real impact on human health on that, and even in a long-term consumption like that. So I think this would be a kind of problem of this foods, but I agree with Federico. We need to find a balance that we can adjust everything on that. Okay, any more questions or comments on that? Okay, so thank you, Federico. And now we have a coffee break, so we return at 10 and 5. Okay, thank you. No, that doesn't.
Can I leave
Yes.
the controller? Thanks a
you,
lot.
Federico. So, Cristiano? Okay. Okay, let's continue then the program. So I would like to invite Valentina to talk about another class, second class in the school. Good, thanks, Valentina.
Yeah. Thank you so much. So I'm back. But this time we don't talk about salmonella. We are going to talk about microbial community. Okay. We are going to start from something that should be very familiar for you students if you at least take a class in macrobiology. Right, so this is an optimal growth curve of bacteria. Lag, exponential, stationary, and decline. That's when bacteria are happy, they have all the food they need, they will start to replicate, then there is a saturation point where a number of bacteria and nutrients are more or less in an equal way, and then they start to die. Do you think we want something like this in our food? Do we want microorganisms very happy, growing? Depends on the food. Maybe in the yogurt, where I need lactobacillus and streptococcus, but do I want a lot of bacteria in my meat or in my produce? No. So there are some intrinsic and extrinsic factors that influence the growth of bacteria. Think about lemon, okay? Very acid. We are gonna find not a lot of microorganisms. If you have your lemon and you leave it on the counter after a couple of days or weeks, you are gonna see a white layer, right? That's a mold. So the pH of the lemon, for example, doesn't allow Listeria to grow very well. Why do we put food in the fridge? Because low temperature usually decrease the growth, slow down the growth of bacteria. Why do we use alternative packaging and atmosphere? Because most of the foodborne pathogen likes to live with oxygen. And so taking out oxygen allows them not to grow. So this is why I am a food scientist. This is why I'm trying to kill bacteria on food, because I'm able to manipulate intrinsic and extrinsic factors that allow microorganisms to grow. So every time I apply what we call a stressor during food processing, that can be heat, freezing, radiation, use of chemical, I'm gonna move the optimal growth of bacteria in a phase that we call stress phase, right? And so this stress phase will, as the ultimate goal, to decrease the growth and to kill bacteria. But as I always say to my students back in Kansas, bacteria are very intelligent. So they like to adapt and resist. So instead of dying, most of the time, we are gonna have some suboptimal or sublethal condition where bacteria adapt. And so on the right, we have the optimal growth curve that I just showed you, right? They have enough food, they're gonna replicate, stationary, and then eventually die. But every time I apply a stress, that I mean heat or radiation or low temperature, the bacteria have several ways to adapt to this stress. If the stress is effective, most of the time pasteurization, we obtain death, right? But then there is a phase that is called suboptimum, where bacteria adapt to the stress. So you shake them a little bit at the beginning, but then the second time that you reapply this stress, they're like nothing happened. There is another phase. So let me give you an example. I have 2 kids. One is just 2 years old, right? So we go to the park. He falls down. Nothing happened. He stand up immediately. He adapt to the stress, right? Like nothing happened. Sublingual injury. Instead of standing up immediately, we are losing like five minutes looking if there is blood, if everything is okay. So we have some time to adapt to the stress. If this stress is go even further, we are in a stage that is called culturally but not normally, viable but not normally culturable. Going back to my kids, I took my daughter to ice skating. She broke her leg. For 3 months, she was in a wheelchair. I would say that was the same as viable but not culturable. So she was alive, but she was not able to do much, right? So think about like this when I apply stress to the bacteria, okay? So in this suboptimal and sublethal phase, bacteria are still alive, sometimes metabolically inactive, but when there is the correct environmental condition, they're gonna go back to optimal phase. Because again, the overall goal of bacteria is to replicate, so they adapt. Okay, so this is kind of summary of what's happening when I apply stress. I told you, bacteria want to survive, and most of the time, what happens is there is a change in metabolism, okay? Other time, they sporulate. Think about Bacillus cereus, think about Clostridium. They feel in danger, they will form spore, and they're gonna wait the correct time to germinate and reproduce again. What we are gonna talk today is the third way that they have to adapt to this stressor, and is biofilm, formation of biofilm. Now, how many of you ever heard about the term biofilm? All of us have biofilm, or the majority of us have biofilm on our teeth. Think about when you wash your hands in the sink, in the bathroom, in the drain are full of biofilm. So biofilm are not important only for food. They are an issue in a lot of industry, and they are everywhere in the environment. These are 2 pictures to show you that we don't see them, but look how dense these biofilm are in a food processing plant. This is stainless steel. And this is instead a salmonella biofilm on cantaloupe. So if I need to define biofilm, it's defined as a community that is embedded in an extracellular polymeric substance that is called EPS. There are 4 main ways for biofilm formation. At the beginning, the cells are going to be in the planktonic stage, so they are still single cell. They are going to find a niche because there is a stressor, because they like to live together, and they're gonna produce a lot of adenosine that they are gonna allow them to attach to this surface. If you are very efficient in your cleaning and sanitation practices, this is probably the only time where you're gonna be able to eliminate biofilm, because after this attachment, the force, the strength is becoming so strong that it's very difficult to get rid of biofilm. And that's because they're gonna start building this EPS, that is a polysaccharide membrane that they make them all stick together. After at least 48, 72 hours, these biofilm are called mature, almost impossible to get rid of unless you scrape, and there is a lot of problem with cross-contamination if you do like this. Sometime in the late phase of biofilm can decide to disperse, so go back to phase 1, single cell, or rearrange their structure based on the stressor that are present in the environment. Now, there are a lot of advantages in living in community. First of all, cooperation. They also filter better nutrient. They have a more efficient way to absorb. They create enzymatic digestion system. Very rarely, I would say, they compete when they decide to live together. Okay, most of the time is because of cooperation, or is because biofilm is like a fortress. So they develop tolerance and resistance. And one of the problems that I'm studying is when these biofilm develop the resistance to sanitizer that we use in the food industry. Okay. So there are a lot of ways to produce biofilm in a lab setting. There is no perfect way. All ways are acceptable. I would say that the important thing is that you justify your choice. I call these 3 devices a static way to produce biofilm. What I mean by static is, and I will show the 3 after, they are dynamic. In this 3 way, one is called the microtiter. All of us probably in a micro lab have a 96 well plate. And you just grow your biofilm on the bottom of your 96 well plate. There is no exchange of media. So for how long you consider your biofilm mature, you are gonna build this biofilm in this well. The Calgary device is the same device, but on top you put the lid. And this system is used to evaluate the minimally inhibitory concentration when you want to understand if an antibiotic or a sanitizer is active against your biofilm. This 3rd method, again, is a static method. There is a bead at the bottom of the well, and this is a pretty cool visual method. So at time 0, you can see the bead, but then when the biofilm starts forming, the beads is not visible anymore because the EPS form around these beads. So this is a very fast and easy way to say that biofilm are formed. The other 3 ways to build a biofilm, I'm calling them dynamic, because the main difference with the previous 3 one is that in this system, I have a continuous exchange of nutrient. So for example, this one is called a deep flow biofilm reactor. I have 6 channels. You see this outlet is where I'm gonna be able to put my media, and I can use 6 different media to grow my biofilm and then evaluate what is the best way to do it. I'm gonna spend more time on this one, so bear with me for the next slide. Then I'm gonna conclude with this flow cell chamber. Again, the media is entering here and is getting out from this outlet, and this system is mainly used to, for microscopy. So you have media coming in and going out, and then these glass slides are gonna be under a microscope. So very useful from the visual and architecture point of view. I want to talk a little bit more about this system, because it's the system we are using in my lab, and it's called a CDC biofilm reactor. It's a dynamic system, is a glass vessel with 8 rods. Each rods have 3 coupons. It's such a small system that I can put it in any incubator, so I can play with material and I can play with temperature. And, oh God, sorry about that. Anyway, this is a dynamic, this is my first time that I decided to turn this thing. Anyway, so we have a first phase that we call batch phase, and is only 24 hours, is when I allow the bacteria to attach to my surface, and then I have a 72 hour of continuous flow phase, where I'm gonna continuously put media and collect, okay? So think about a dairy plant where you have cleaning place, right? Before cleaning place, you have all these tubes where material pass. And this is a good way to build biofilm for that kind of industry, okay? Because I'm giving continuously a shear force environment. This is not working very well, for example, for cereal plant, because you don't want water in a cereal plant, in a dry plant, okay? So if I need to simulate the growth of biofilm in a cereal plant, I will probably use a static, like the 96 well plate biofilm that I show you. Okay. Now, I'm gonna take you out of the animal world, and I know I'm struggling in Brazil with vegetable a lot. You guys eat a lot of meat, a lot of good fruit, but I want always my veggies. So, I recently finished a project for the apple industry in the United States. And this is also applicable to the meat industry, because when you have a small meat processor, sometimes they hang the sausage on wood shelf. Or when you think about a big packing house, you have stainless steel, you have nylon, you have plastic. So my project was in the produce industry, but the same material that I use in my project are also relevant for the meat industry. Anyway, what we study, we try to understand the attachment of Listeria biofilm and the formation in this type of containers. So the first objective was to evaluate the effectiveness of certain sanitizer, and then on surface representatives of the food contact material that they use in the produce industry, and then to validate this thing that we considered in the lab in packing houses. So, as I told you, we use wood, we use nylon, and we use plastic. Again, these three materials are also relevant to the meat industry. So, what we did, we evaluate the attachment of biofilm on these surfaces with a test that we call rinse test. We evaluate the hydrophobicity of biofilm, measuring the contact angle and the strength of the biofilm. We did some microscopy, and then finally we evaluate the sanitizer. Okay, so these are the results for the rinse test. And the rinse test is very easy, but tells me a lot of things. So what we do is we build this biofilm, and then we do a dip in 3 different beakers where we try to understand water, right? And we try to understand how many bacteria are in the water, so they detach, and how many bacteria instead are sticking to the surface. And so you can see that after 2 hours, we have a significant higher number of bacteria on nylon and wood as compared to plastic. This is key because what this means is if in my plant I have a lot of plastic surfaces, if I clean regularly, I still have the opportunity to get rid of biofilm because the load on plastic material is still manageable. But more the time pass on nylon and wood, the attachment is higher. And so if I do not clean regularly these surfaces, the possibility to get rid of biofilm is very low. Okay, so from the sanitary point of view, if I have the possibility to choose, let's not choose nylon and wood. Let's choose plastic because it's better for cleaning and sanitation. And this is maybe seems very obvious to us, but it's not obvious or is not easily adaptable to an industry that for 50 years they are collecting their apple in wood bins. It's not because Valentina did this rinse essay that they're gonna change their mind. And I got a very clear answer saying, these wood bins cost me a lot of money. It's 50 years that I have it. I'm gonna keep it until they get broken. So my answer to them is, yes, I understood. Is a lot of investment. Please, when you get at the end of the life of your wood bin, don't buy again wood bin, buy plastic bins. Because the ability that you have to clean those containers is higher. The other thing that we did was trying to understand the hydrophobicity of the biofilm on the different surface. And what this information is telling me, measuring the contact angle, is how well these bacteria spread on the surface. And if they spread very well, it also means that they attach very well. So, 2 different pictures. If they have a low contact angle, they are spread and they have high surface energy. If they have a higher contact angle, you see this is like really the bubble, and they have a low surface energy. So, keep in mind what I just told you about the rinse assay. It seems like the bacteria on wood and nylon stick better as compared to plastic. So I am expecting to find a low contact angle on wood and nylon because they spread better as compared to plastic. And this is what we found. Based on the time, wood was always lower as compared to plastic. And then we just used two different solvents, water and formaldehyde, just because they have a different polarity. And we wanted to understand if the property in these two solvents were different. But the end message is low contact angle for wood and nylon, and depending on the time. So we kind of confirm what we saw in the rinse essay. So because we are scientists, we were even more curious, and so we did some microscopy. And you can see here, this is an SEM picture, where you can see nylon, that is a fabric full of threads. And this is what's happening from the architectural point of view when Listeria monocytogenes forms biofilm. There is an immediate microcolonization of all the surface. And then you see that after 24 and 96 hours, the matrix just grow. Very similar to wood. This time, you see that there are a lot of pores here, so wood is not uniform. This is, to me, is pretty cool because it's when our technician help us to do the microscopy, you can see that there are black spot. That means he wasn't able to catch the biofilm. Probably the biofilm is down penetrated in the wood. That's why we couldn't catch it. But then again, after 24 hours, there is a complete colonization of all the surface and then a growth of the entire matrix. On wood and nylon, this is not how, from the book, you want biofilm to grow. But if you look at plastic, this is by the book, the classic way that biofilm will grow. And the difference is the topography of the material. Plastic is uniform. There are no pores. There are no threads. And so bacteria start with microcolony, and then they aggregate to form microcolony, and then after 96 hours, there is a complete colonization, and the biofilm is mature. And again, the difference is the topography of the material. Okay, then the last thing that we did for this first study was let's see, what are the interventions that I can use with this material in order to get rid of biofilm. And so we were not very creative in the intervention because we wanted to offer a real solution to our stakeholder. And so what we did is probably most of the intervention that are also allowed in Brazil, where you use chlorine or chlorine dioxide, that is a gas, steam, peracetic acid, and then we use a silver dihydrogen citrate that is a ready-to-use antimicrobial. And the concentration are the concentration that are allowed in the food industry. The time was just 1 minute and 2 minutes. That's because people want very fast solution, right? They don't want to lose 10 minutes to spray, lose water, lose time. They want something very fast. Okay, let me see if this time is working. So, this is what we call box in my lab, where we are able to spray our chemical. And this is the rod of the biofilm reactor. So we have a spray, and then we have a hole, and then we are able to turn our coupons. So on both surface, we have the treatment. This is instead when we apply the steam, okay, so just a steamer. And this is instead when we apply chlorine dioxide. And instead of, I don't know if you guys are familiar, is a gas. There are a lot of concern for the safety of the user. And so what we did, we contacted an industry that have a particular technology where you just mix two pouches, so an activator, and the chlorine dioxide, and the gas will form. And so we were able to apply the gas in a small chamber, so everything was contained and controlled. What we found, everything was significant. That means, depending on the sanitizer, depending on the time, depending on the surface, we were able to see more or less efficacy. And so if I need to report you from an inactivation point of view, what we observe is that with chlorine dioxide gas, everything was below detectable limit. And that's because of the ability of this gas to penetrate in those spore and threads that I show you with the microscopy. PAA was the sanitizer that worked best. Steam worked okay, mainly in plastic and nylon. We observe, of course, a effect of time. More you apply your sanitizer, more you apply your intervention, higher the reduction. Overall, plastic was the one that worked, any intervention worked the best, and then nylon and wood. So the other thing that we did is say, okay, what are we gonna do with this data? We already told them that if they can, do not use wood, but they use it. They have it. So let's try to go to the commercial apple orchard or packing houses and see with what we did in the lab if we can still help them. And so we selected two of the intervention that we evaluated in the lab, the chlorine dioxide gas, because it was the one that worked the best. And the other thing that we did is try to offer them a solution that was already ready, and they didn't need to mix it with water like you will do with chlorine or peracetic acid, because this product is, you just spray. You will see in a second. And so we went around the United States, not really, but mainly in the Midwest and in the West Coast. That's where a lot of apple production is. The West Coast representing very big apple production. Iowa and Michigan are not, is middle size. In Kansas, we're just starting. So we just wanted to give them an idea of, are the intervention working also in different size of production. And so what we did, we say, okay, there are some facilities that are gonna be very good and clean routinely. And so we produce what we call sessile cell. So we just grow them for 24 hours and we challenge our surface with these bacteria that will grow for 24 hours. But we also know, for example, in Washington, that because of the production volume, they're not gonna have time to clean every day like they can do in Kansas, where the production is very little. And so we say these people might only clean at the end of the week. So what's happening if I grow what I call biofilm for more than 24 hours? And so we went up to 72 hours. And then we couldn't bring foodborne pathogen in this facility. And so what we did, we used some surrogate that were antibiotic resistant. So we were able to catch them in the microflora. Okay, so you can see how big these crates are. I mean, and so these one were the wood, and then we had the plastic, and these are the bag of nylon. And so we went to this facility, and this was the chlorine dioxide application. When we use bags, we were able to put it in a box and contain everything. When instead we have those big wood basket, we needed to cover everything with like a hand, and then we had the monitor where we check the level of chlorine dioxide. And instead, here, you see we did the same thing, but this time we apply the ready-to-use sanitizer. So this is Savannah. Again, I'm sorry because this is Savannah just spraying in the silver on the bags. Oh, yeah, results. So disclaimer, we went there during early summer, and the summer in the West Coast, that is a desert, is very different than the summer in the Midwest. So when we decide the timing, we didn't think that the West Coast is desert. And I'm telling you because these results kind of show that the environmental conditions were very important. So this is what happened when we went in the Midwest, and I apply silver and chlorine dioxide. These are the bacteria grow for 24 hours. These are the biofilm. You can see again chlorine dioxide is able to reduce everything below detectable limit. Doesn't matter sessile or biofilm. And instead we have more than 2 log reduction with the silver. So not bad results. But then when we went in the Washington area, things didn't work as well as in the Midwest. And so the two main difference. The facility in the Midwest were relatively small, and they were a closed environment. So the temperature was relatively controlled. In the Washington area, these facilities are so huge that it's almost impossible they are open. So they're not temperature controlled. And so the hot temperature and the low humidity influence a lot the ability of chlorine dioxide to decrease bacteria. So kind of interesting results in saying maybe the environment is going to influence what I can use and where. So conclusion, we saw that cells are able to grow and strongly attach on wood, nylon, and plastic. There are different accumulation, different topography, different biofilm architecture, depending on the material. The sanitizer that we use had very little effect on wood, better in nylon, good, very good on plastic. And then the overall message for our stakeholder is when you choose the sanitizer, you need to think which material you want to clean, because there is an interaction and an effect on the effectiveness of your sanitation. Okay, questions? Sorry. Thank you.
Thanks, Valentina. We have time for questions. Anyone would like to ask something? Marcos, you got it?
Hey, Valentina, thanks for your presentation. So, when they go to those big crates, and you're talking about sanitizing the crates, right? So when they go to the packing plants, would those apples be washed again or sanitized again? Because then they go to those small plastic bags, and then you get to the consumer. My question is, are those biofilms carry over all the way to the consumer, or are they washed again? And how safe are we? Because in the US, we don't wash anything, right? Well, I do, because I'm from Brazil, but the Americans don't, right? Overall, the overall thought is that you go to those pre-processed food, you eat it as is. So what are your thoughts about it?
Yeah, so let me tell you, do you buy the ready-to-eat salad that they say they're triple wash? I mean, you can test them. They're full of, I would wash them. Yeah, so what's happening, yes, we wash the apple. There is a water tank before packing where you wash the apple. What's happening is that when, like 5 or 6 years ago, there was an outbreak with caramel apple. And so what happened is the cleaning didn't work very well. There were still bacteria on the apple. They put the stick of wood. They allowed listeria from the exterior to go inside the apple, and people got sick. So we recently had another outbreak similar with peach. And so what's happening, even if there is a cleaning step in the packing house, the fact that these beans or the harvesting tool are not cleaned continuously, there is a risk based on the outbreak that we are having in the United States, that there is a cross-contamination. And so that's what we are, like the feed to fork. We know that the washing the carcasses work, but can we do also something before if there is a step in the packing house or towards consumer that doesn't work? And so cleaning and washing the container reduce the potential level of listeria on those fruit that then are going to be washed again. Yeah. But I'm with you. After we did an experiment in the lab where we check the triple wash salad, we saw so many background microflora that I say, let's wash it.
We were discussing exactly like this situation, right? There's a thing related to eating habits. So if you receive the vegetables fresh, here in Brazil it's very common that we buy fresh directly from the producer. So it's natural that you wash many, many times. So it's a kind of eating habit that we have. And if you take a look in the major outbreaks that you have recently in US, there are a lot of vegetables related, right? And so there's a kind of feeling that, okay, it's minimally processed, so it's washed, so it's safe to eat, and sometimes they don't even wash in their homes. So it's a kind of, this happens. Okay, any more questions, Anka? Okay.
Thank you, Valentina. Very nice, very pedagogical talk. A question about the surface. Did you try or did you heard about the surfaces with nanoparticles to avoid the adhesion? Maybe it's expensive, but could be efficient, I think.
Yes, so there are a lot of groups working on that. I saw a study that show that what I call sessile, so planktonic cell, are prevented. Is we are doing a study with those type of surface, and I'm not sure because of the EPS of the biofilm if they are gonna work. I also saw some group, I think it was Cornell, that has an enzyme, and so they think that enzyme is more efficient in degrading and breaking the EPS. But yes, there is a huge interest because I don't know in Brazil, but in United States we are towards clean label, and so people are trying to avoid the use of chemical a lot. So that's a good. Yeah, thank you.
Nowadays in Brazil, this is becoming more and more common.
Yeah.
This clean food,
Clean
something
label.
like this.
Yeah.
Okay. Okay.
Sorry for asking you too many
No.
questions. Okay, a very different question. You let me know if that is not under your area. But I found your gas study like very interesting, and I was wondering about milking parlors on dairies. So, for instance, I visit several dairies that like the cleaning system usually works, but we have a lot of problems with biofilms in the pipeline at the milking parlor. And for instance, our dairy at WSU, they have a lot of 90-degree joints, and that tends to form a lot of biofilms. So our coliform count, they all go up, and like fluctuates, go up and down a lot of times. With a gas system too, like you would wash it, but then you do an additional cleaning with gas. Do you think that will help with removing those biofilms in poorly designed milking parlors in dairies?
Yes, coupled with a partial disassemble of the pipes. That will work. And maybe I have a question back to you. The meat industry and the produce industry are very concerned about biofilm. I know in the dairy industry is a huge problem, but the money that circulates to solve this problem are not the same. So why is that? Yeah. So it's, from the funding point of view, it's very interesting to see that the meat and the produce industry are investing, and instead the dairy industry is not, at least funding-wise. Maybe industry-wise is different.
So from the dairy perspective, especially milking parlors, we have like 3 or 4 companies, right? We'll have De Laval, Lilly, Biomatic, Gia, and that's it. So maybe from the funding perspective, maybe the governmental agencies think like these companies should fund this kind of research. The problem is that they don't, right? So we have a problem. It's very present in most of the dairies, and there's no research to do an actual job. And that's what they are recommending, exactly what you said. You should like, detach or disassemble, clean it by hand, those like biofilms, but you have a dairy that is working 24/7 and you're milking 5,000 cows per day. You don't have time to do that, so the problem persists.
Okay. Any more questions? Okay, then. Valentina, thanks a lot for your class. Thank you. Okay, as I said in the beginning of the activities today, unfortunately, Hilario was not able to come, but then we can finish the activities right now, and we will return at 2 p.m. sharp, okay? Thanks, everyone.